So let us say we have a 2 gray surface enclosure. We have a 2 gray surface enclosure. Okay. Okay, so this is surface 1, which is maintained at temperature T1, and let us say the area of that surface is A1, and let us say that the emissivity is epsilon 1. Okay. And similarly, you have another surface which is T2, A2 and epsilon 2. Okay. So, I want to find out the net radiation exchange between these two surfaces. Okay. How many resistances are there? How many? Yeah? 6. Why is it 6? Okay. Okay. So, every surface okay. So, supposing if the black body temperature of the black body radiation of the first surface is EB1, okay, and the black body radiation of the second surface is EB2, okay. Now, if I maintain the two at the same temperature, okay, what will be the emission or what will be the radiation exchange between itself? Suppose I maintain it at the same temperature, okay, the whole surface is maintained at the same isothermal temperature. So, what will be the radiation exchange? This is total quantity, right? We are looking at J1 and J2. We are looking at J1 and J2. So, what is it function of? It's function of temperature and anything else, or that's it? This is total quantity, right? So, this is integrated over all angles and it's integrated over all wavelengths. So, this is only a function of temperature, correct? So, if it's a function of temperature, then what will be the radiation exchange between itself? Net radiation exchange between itself will be 0, right? Because the amount that is emitted from one location to the other location is exactly the same. And so, the net radiation exchange, so note that you may have a small differential element whose view factor with another differential element here could be different, but the net radiation exchange over the whole surface within itself is going to be 0 because you are maintaining it at a constant temperature. Okay. So, therefore, the total number of resistances will boil down to 3. So, this will be J1, J2 and EB2. Okay. So, what are these resistances? What is this resistance? What is this resistance? 1 minus epsilon 1 by A1 epsilon 1. And what about this resistance? 1 upon A1 F12, and this is 1 minus epsilon 2 by A2 epsilon 2. Okay. So, now simply based on the resistance concept, so if Q1 is the net radiation exchange between the two surfaces from the surface 1, okay, then Q2 will be, what will be Q2? So, this is the net radiation exchange with respect to surface 1, right. So, what is Q1? Q1 is the amount of heat either released from 1 or it is supplied to surface 1 in order to maintain a constant temperature. So, what should be Q2 then? It will be minus Q1, right, because it's just, there are just two surfaces. and both are maintained at constant temperature. So, first from simple energy balance it will be Q2 will be equal to minus Q1. Okay. So, from here Q equal to Q2 equal to minus Q1. So, based on resistance networks we can simply write it as EB1 minus EB2 divided by the total resistance. Okay. So, the resistances are in series. So, the total resistance is the sum of individual resistances. So, therefore, Q will be sigma T1 to the power of 4, T2 to the power of 4 divided by 1 by A1 F12 plus 1 minus epsilon 1 by A1 epsilon 1 epsilon 2 by A2 epsilon 2. Okay. So, that is the net radiation exchange between these two surfaces. Okay. So, let us add a little bit simplification here. Suppose if the enclosures are parallel to each other, suppose the two surfaces are parallel and infinitely long. Okay. Okay. So, if it is parallel and infinitely, so it is essentially a parallel plate. So, you have parallel plates and this is maintained at temperature T1, maintained at T2, and the emissivity is epsilon 1, epsilon 2, and the area is A1 and A2. Okay. So, if it is infinitely parallel, then you could assume that these two areas are equal to each other. So, therefore, so it is the same system like what we looked at short while ago, except that it is infinitely parallel, long and parallel now, and so the radiation exchange is still the same. So, it is sigma T1 to the power of 4, T2 to the power of 4 divided by 1 by A1 and A2 are same. So, we can take it up there. So, if I say area of the parallel plate is A, so that will be 1 by F12 plus 1 minus epsilon 1 by epsilon 1. What is F12? It's 1, because whatever radiation that leaves surface 2, it has to be seen by surface 1. So, therefore, so the net radiation exchange will be A sigma T1 to the power of 4 minus sigma T2 to the power of 4 divided by 1 plus 1 by epsilon 1 minus 1 epsilon 2 minus 1. So, that will be A sigma T1 to the power of 4 divided by 1 by epsilon 1 epsilon 2 minus 1. So, that is the net radiation exchange between two grey surfaces. So, note that if they were to be a black body, what will happen? The emissivities are 1, right? If it is a black body, emissivities are 1. So, if it were to be a black body, surface is black body, then emissivities are 1, and so this will simply become sigma A into T1 power 4 minus T2 to the power of 4. This is the classical relationship that all of you have seen, right? So, remember that when you have radiation exchange which is infinitely parallel and the U factors are 1, this is the radiation exchange between the two surfaces if it were to be a black body. So, that comes out clearly from the expression that we actually derived. So, this is an important thing you should check whenever you have a real surface, whenever you derive the net radiation exchange for a real surface, it is actually useful to check the corresponding relationship and see if it actually boils down to the corresponding black body relationship if you assume all the emissivities to be 1. Okay. It is a very good thumb rule to check, you know. If you put F12 as 1, it becomes parallel. So be careful. You can put epsilon as 1, that is correct. Then the surfaces are black body. But then if you put F12 as 1, you also have to put the areas to be 1. Areas to be equal, not 1. Right? You understand? So the areas and the view factors, they are obviously correlated. You cannot completely separate the two and assume, make some approximations for each of them. So if the area is going to change, then there is some effect on the view factor, because the view factor already contains the integral over the whole area, right? So area is already taken into account in the view factor. So we are going to look at a little bit more extension of this radiation shield. So this is a very important aspect of quantification of any radiation system. So for example, if you have a nuclear reactor, okay, now you do not want any of the radiation to leak out of the system, right? You do not want radiation to leak out because it is hazardous, right? So what happens in radiation when it leaks is that, particularly for human beings, one of the first things that gets affected is the thyroid gland. So you know, how many of you have heard about thyroid gland? Oh, most of you. So the first thing, one of the first things that gets affected is the thyroid gland. That's because the iodine which is present in the body, so the radioactive isotope of iodine is something which can be very easily triggered. So whenever there is an exposure to radiation, one of the first things that gets triggered is actually the normal iodine gets converted into the radioactive form of iodine. And so that hurts the thyroid gland very easily. So that's why when there is a radiation exposure, a couple of things that is generally done is they ask people to drink a lot of milk, which is again radiation free milk. So that somehow seems to protect the thyroid gland. I don't know how, but somehow it does. So that's one thing. And the second thing is you know, cover the neck as far as possible, because the thyroid gland is actually sitting in the neck here, right? So these are the two general suggestions that's given. So anyway, so radiation shield is actually very important, because you do not want radiation to leak out from a nuclear reactor or some other system where radiation is active. Okay. So the way it's done is, let's take a very simple case. Of course, the real life system is not as simple as this. So the way the radiation shield is actually designed is by playing with the emissivities of that surface. Okay. So we will look at only gray surfaces here. Of course, one could derive all the relationships for a normal surface, but we will not do that in this course. Okay. So the way it's done is, we tweak the emissivities of the surface. Particularly emissivity. We tweak the surface properties. So supposing we have one surface which is maintained at temperature T1, and let's say you have another surface whose emissivity is epsilon 1, and it's emitting radiation in the inside of that particular surface. Let's say that there is no radiation on the other side, okay? Or let's say there is a reactor sitting on the other side. So what is relevant is only radiation which is emitted by the outer surface of that particular object that we are looking at. Okay? And let's say this is the receiving object, which is, let's say, at temperature T2 and emissivity is epsilon 2. So we need to place something in between in order to protect the second surface from receiving the radiation emitted, or minimize the radiation that is received from surface 1. Cannot be completely 0, but you minimize it as much as possible. And the way it's done is, you put a finite thickness material, a surface which is in between. Let's say it's a parallel plate. Okay. Then, if let's say the emissivity, I call this surface 3, which is at, let's say, temperature T3. So I create the surface. Maybe I paint the surfaces, two surfaces in some other way, or I alter the surface roughness of that surface as such that the emissivity of the two sides of the same object is different. Okay. So, I create a system where the emissivity of one side is completely different from the emissivity of the other side of the same object. So, that way I can actually cut down the total amount of radiation that is actually transferred from 1 to 2. Why is that? Because the resistance that is offered by the surface to exchange radiation or to emit radiation from the surface, it depends upon the surface properties such as emissivity. So, we know that the resistance offered by the surface is 1 minus epsilon by the area times epsilon. So, by playing with the value of epsilon, we should be able to control the total amount of radiation that is emitted by the outer surface of that particular object. So, if you want to characterize this, we can now use the resistance network concept. How many resistances are there here? How many resistances are there for this system? 6. What are they? Okay. So, there is one resistance for radiation that is emitted by surface 1. There is one resistance for exchange between surface 1 and the surface 2 which is facing this surface, and then there is exchange from the surface resistance of 31 and there is surface resistance of 32 and resistance between the two surfaces and the other one. Okay. So, there are totally 6 resistances. So, this is EB1 and this is EB2, okay. This is J1, J2, J3, that is on the side which is facing surface 1, and this will be EB3, that is the corresponding blackbody radiation for the third surface, and this is J32 and this is J2. Now, here of course, I have assumed that the resistance for conduction is negligible in the third surface. All radiation that actually goes from 1 to 2 will be from 3. There is 0, yeah, that is right, the view factor is 0, correct, because of the view factor. Now, supposing if the shield that you have placed does not completely cover the two surfaces, then there will be exchange between 1 and 2. So, this is 1 minus epsilon 1 by A1 epsilon 1, this is 1 by A1 F13, this is 1 minus epsilon 3 by epsilon 31 by A1 A3 epsilon 31. So, note that the emissivities now on different sides are different. So, you have to account for that in the resistance is 32 by A3 epsilon 32 and 1 by A2 A3 F32 and will be 1 minus epsilon 2 by A2 epsilon 2. Okay. So, now we can find the net radiation exchange between the first and the second surface. So, that will be EB1 minus EB2 divided by R total. So, if you have the resistances in series, that is the total resistance, and so that will be sigma T1 to the power of 4 minus sigma T2 to the power of 4 divided by 1 minus epsilon 1 by A1 epsilon 1 plus 1 by A1 F13 plus 1 minus epsilon 31 by A1 epsilon 31 A3 plus 1 minus epsilon 32 by A3 epsilon 32 plus 1 by A3 F32 plus 1 minus epsilon 2 by A2 epsilon 2. Okay. So, what is F13 and F32? If it is a parallel plate, view factor is 1, right. So, therefore, F13 equal to F32 equal to 1 and A1 equal to A3 equal to A2. Okay. So, if you plug in all these factors, so you will find that the net radiation exchange Q is given by sigma T1 to the power of 4 minus T2 to the power of 4 divided by 1 by epsilon 1 plus 1 minus epsilon 31 by epsilon 31, 1 minus epsilon 32 by epsilon 32. Okay. I mean, that is the net radiation exchange between the two surfaces 1 and 2. So, clearly you can see by tweaking epsilon 31 and epsilon 32, you can actually minimize the net radiation exchange between 1 and 2. So, that is the concept of using this radiation shield. Okay. Alright, so I think it is a good point to stop. So, there are a couple of small topics in radiation that we will finish in the next lecture. So, one is the re-radiating surface and one is the effect of, the next one is the effect of medium. So far we never considered what is the effect of medium that may be present between the two surfaces. So, we will try to quantify that in the next lecture.